All right. So yeah, moving on. I am Isaac John. I am a PhD scholar from IIT Palakkad. So I work under the supervision of Dr. Shantakumar Mohan, and as you might have known, he's also basically the faculty in charge of this course, ME79, Mechanics and Control of Robotic Manipulators. So yeah, for the duration of this course, every week we'll have this 2 hours of live discussions regarding the topics that we discuss on each week. We'll have a brief summary of the topics that we have discussed in every week, and we'll also solve some sample tutorial problems that could be useful for you to solve the quizzes as part of your certificate program. So before starting the session, there could be chances that my connection may get unstable because at the moment I don't have a very good internet facility. So if in case if something is not clear, if whatever I have said is not clear, or if the clarity is not good enough for you to follow through, please let me know. I'll happy to uh, revisit the topics, or I'll happy to repeat the things that is not clear again as well. All right. So yes, I hope we can begin the session from now onwards. Yes. So in this tutorial, in this live session, we'll be covering topics regarding the kinematic parameters. So as you have known, we have in week 2, we may have discussed. Am I audible? Can anyone hear me?
Yes,
Hello.
sir.
Okay. Yes. But yeah. Okay. So moving on. I hope you have gone through the assignments. Like, have you solved the assignments on week 1? Any difficulties with week 1? I guess you still have deadline up to 9th of August.
Yes, sir.
Okay,
I have
so
12
okay, so I hope you have gone through all the lectures of week 2. So yeah, so we'll first cover some topics, or we'll summarize whatever we have covered in the lectures, some key topics. So as far as this week is concerned, the entire topic deals with kinematic parameters and one, as you call this, DH parameter. So this is one of the most fundamental problems in mathematical modeling of a robot. Like it helps you to geometrically model any robot, any serial robot, comprising of binary links and single degrees of freedom joints. So it's very important that you learn whatever that has been taught in the week, especially the DH parameters, the conventions of the DH parameters, how to assign frames on a given robot, how to identify the DH parameters. So yeah, if you crack whatever that is being taught in this weekend, the subsequent weekends will be very easy. Like it'll be very easy to follow through the topics that the later weeks will be covering. Okay, so moving on, basically the key topics that we have discussed for this weekend are for this week are basically the kinematic parameters and the DH representation of robots. DH representation, there are multiple representations. If you can recall the lectures, we have covered in detail something what we called non-standard DH parameters. I hope you would recall this. Non-standard DH parameters. And you might also wonder if there exists any standard DH parameters. Yes, obviously. Standard DH parameters. And based on the advantages that the non-standard parameters offers, this is what we follow throughout this course. So in line with the course is what this is. Like both of them have their own advantages and disadvantages, but due to the fact that the advantages of the non-standard methodology far outweighs what is being offered by the standard methodology, we stick with the non-standard representation for DH parameters. And we'll also cover some examples regarding frame assignments of different robots. And later, once we have covered the summary of the topics, we'll also discuss some sample problems. Okay, so moving on regarding kinematic parameters. What it tries to convey is the choice of coordinate frames and location of the coordinate frames. So as you might have observed, or as you might have understood by now, a robot basically consists of rigid bodies. So for example, if I'm taking a 2R robot, it comprises of two rigid links as shown here. This is what we call a 2R robot because it has two revolute joints, a revolute joint over here, a revolute joint over here. So if I'm attaching the coordinate frames, it would look something like this. The global coordinate frames would look something like this based on right-handedness, right-hand coordinate system. Z0, X0, Y0. This is link 1. This is link 2. So yes, as you might have observed, a robot comprises of two elements primarily. Those are the rigid links. So this is the first link and this is the second link. And the rigid links are basically constrained by what we call joints. So over here is one joint, a revolute joint, if you can see. And over here is the second joint. I suppose there is some latency issues with my voice and what is being displayed on the slides. Is that correct? There should be some latencies issues. Okay.
Yes, yes.
Okay. Okay. So, but anyways, if you are if the discussion is not clear, please let me know by audio. I'll be happy to repeat that. No problems. No worries. Okay. So yeah, moving on. We have this is just a 2R robot. As an example, I am providing an example of a 2R robot, right? Comprising of two rigid bodies and two joints. So this is the first joint, a revolute joint, and this is the second revolute joint. And these two links, the second and link 1, are constrained to move in a plane using the two revolute joints. All right. So in mathematical modeling, what we do is that instead of rigid, we represent rigid bodies using reference frames, right? So the entire properties of a rigid body, like be it center of mass or moment of inertia, all these things can be represented using reference frames. So the whatever we have attached over here, this x0, y0, z0, this is a reference frame corresponding to the ground, and we'll also have to attach a reference frame to represent the first link. So mostly it will probably coincide with uh, the the zeroth reference frame, x1, z1, y1. But how to assign this reference frame, we'll come that in later slides. And for the second link, we'll have another reference frame, z2, x2, y2. So a position of a robot, position and orientation of the end effector are basically conveyed through the relative transformation between the reference frames rather than rigid bodies. And how to model or how to attach these reference frames and what are the conventions that we use to make transformations from one reference frame to the another is what we were dealing throughout the duration of this entire week, right? So we'll basically revisit all the topics that deals with the assignment of the reference frames as well as the parameters used to define the transformation between among the reference frames, right? So depending on the conventions used, the number of reference frames would also be different. So for example, if you take a look at the first point, it says for an ND of manipulator, n plus 2 frames are required to fully define the pose of the end effector with respect to the fixed base. So this is a very important point. So if the degrees of freedom of a robot is n, we would require 2 more additional frames so that the transformation of the end effector can be represented with respect to the fixed base. Right. Again, if I'm bringing an example of this 2-hour robot, a 2-hour robot has 2 degrees of freedom, 2 degrees of freedom. This is first link. This is the second link. And since there are 2 rigid bodies, since this is a 2 degrees of freedom mechanism, we would require 4 reference frames. So we would attach 1 reference frame to the ground. Ground also requires a reference frame. And the second reference frame would be on link 1. The third reference frame would be, the third reference frame would be on link 2. Link 2. And the fourth reference frame would be on the end effector. So in addition to the 2 frames that we attach on the links, so if there are 2 links in addition to the 2 reference frame we attach to the links, we'll also attach 2 more reference frames. The +2 component comes from this end effector and the ground. That is where the +2 component comes from. All right, so and moving on. So like we'll also have to discuss the second point also. Apologies for that. What does the second point say? The second point says that as per the classical mechanics principle, we would require 6 times n+2 parameters. 1 second. Okay, so with respect to the second point, it says as per the classical mechanics, as per the classical spatial mechanics principle, we would require 6 times n+2 parameters. So why do we require 6 times n+2 parameters? Because as you might have observed, a rigid body in space would have 6 degrees of freedom, right? A rigid body in a space would have 3 translations and 3 rotational degrees of freedom. And due to the fact that we have n+2 frames, we would require 6 times n+2 parameters to represent all the configurations of all the frames. We would require that many degrees of freedom to fully define the configuration of n+2 frames. So now what to do? If we require 6 times n+2 parameters, this is where the DH approach comes in. A DH approach basically simplifies this problem. We would require lesser than 6 times n+2 parameters. So a brief introduction to the DH parameters. This was introduced by Jacques Denavit and Richard Hartenberg. So Denavit is a scientist from France and Hartenberg is from US. So they basically introduced a convention in 1955 in order to standardize the coordinate frames for spatial linkages. So it was introduced by the 2 scientists, Denavit and Hartenberg, and this is how the convention that we discussed throughout the lectures got its name. And coming on to the second point, it says the DH parameters are 4 parameters. So instead of using 6 parameters, they are only using 4 parameters. So that greatly simplifies the problem. So the DH parameters are 4 parameters associated with the particular convention for attaching reference frames to the links of spatial kinematic manipulator. So what it essentially says that if we stick to a particular convention in assigning the reference frames to each of these links, we would require only 4 parameters. So if you are randomly attaching frames on the without following any convention, if you are randomly attaching reference frames, we would require 6 parameters. But if we are assigning the frames as devised by Jacques Denavit and Richard Hartenberg, we would only require 4 parameters. And how to do so, we would discuss that in the coming lectures. You might have already gone through in the during the weekly lectures by Professor Shantakumar. Yeah, I hope we can also revisit before moving on to the problems. Okay, so moving on to the third point. So out of the 4 DS parameters, it can be further segregated into 2 categories, called the first category being link parameters, right? The link parameters which represent the information between 2 consecutive joins. So it's a bit easy to get confused because it says the link parameters are used to represent the information between 2 consecutive joins. And the second category, called join parameters, are basically used to convey the information between 2 consecutive links. Right. This is as per the definition, and it'll probably make sense as we go through the definition of the different kinds of link parameters and join parameters in detail. Right. As of now, it seems counterintuitive because we are using link parameters to represent the relation between 2 consecutive joins, and we are using join parameters to represent the information between 2 consecutive links. Okay, so what are the link parameters? So there are, out of the 4 DS parameters, there are 2 link parameters. So out of which the more detailed definition of link parameters are as follows. It basically specifies the relation, the relative position and orientation between 2 successive joins. So for example, if we have 2 joints axes, like let this be joint axis I, and let this be joint axis I plus 1. So there is basically an orientation difference. So if I bring the I plus 1 joint over here, over to the ith joint, if I try to make it coincide, right? If I'm trying to move it over here, maybe to make it more clear. This is I plus 1 joint. Obviously, there is an angle between I and I plus 1 joint. And there is also an offset, a distance between the 2 joints as well. So we use these link parameters to fully quantify the position and orientation between 2 successive joints, which are the first one being the link twist angle. That is basically the angle between the zi frame and zi minus 1 frame along xi minus 1. So to give more context, let us assume two reference frames. Let this be zi minus 1. Let this be xi minus 1. Let this be yi minus 1. And we have a different reference frame. Sorry, I'll use a different color. This is zi. This is xi. This is yi. So the link twist angle over here, the first one, alpha I minus 1, is basically the angle between zi minus 1, this axis, and zi, the angle between zi minus 1 and zi with respect to xi minus 1. So that is what we represent using link twist angle alpha I minus 1. And the second link parameter is something called the link length. That is the perpendicular distance between zi minus 1 and zi along xi minus 1. Right? So the link parameters are represented with respect to xi minus 1. Here as well as here, you would see the common term being xi minus 1. The twist angle is basically the angle between zi minus 1 and zi. And the link angle is the distance, the perpendicular distance between zi minus 1 and zi. Right? Yes. And moving on to the second set of parameters, kinematic parameters, is what we call as join parameters. This basically specifies, again, this also specifies the position and orientation, but here the difference is, this is with respect to links. Earlier it was with respect to joints, now it is now with respect to links. So the joint parameters basically represents the position and orientation of two successive links. So the first one being the joint angle represented using theta I. This is actually the angle between xi minus 1 and xi along zi. And the second one being the joint distance, that is the perpendicular distance between xi minus 1 and xi along zi. So similar to what we have seen earlier, the common term is basically zi actually. So the joint parameters basically represents the position and orientation with respect to the common axis zi. The joint angle is basically the angle between xi minus 1 and xi. The joint distance is basically the perpendicular distance between xi minus 1 and xi. Both are referenced with respect to zi. Right? So yeah, moving on to the DH representation. It basically deals with two steps. The first step is assigning the frames, how to assign the reference frames on each of these links. And the second part is basically the identification of the DS parameters. So in short, there are two steps. Step one being fixing reference frames on links. And the second stage comes as identification of DS parameters. So over to your right-hand side is basically a generic representation of two links. We have two links basically, link I minus 1 and link I. So the purpose of using DS parameters is to represent the transformation between I minus 1th frame to ith frame. So in the last week, you might have come across how to represent the transformation frame. A transformation matrix would look something like this. From a transformation from I minus 1 to I is basically a 4x4 matrix comprising of a 3x3 rotation matrix, a 3 cross 1 position vector, and the final row would be 0, 0, 0, 1. Right? And a DS parameter is basically employed to create such matrices so that the transformation between successive links can be easily mapped. Right, so we'll get on to the first step regarding how to attach the frames. So if I take a link, a general link as such, a binary link, I hope we are familiar with the definition of binary links. A binary link can connect to another binary link using a single join. Like it can only successively connect to another join. It can only have two joins, right? So if a link is something like this, if it has three joins, then this is no longer a binary link. If it has only two joins, this is basically a binary link. And a binary link has two joins actually, to connect to the links before it and to connect to the links that comes after it. So a common terminology to identify both of these ends used in robotics are the end that is closer to the base. So if if the direction towards the base is here and the direction towards the end effector is here, end effector, the end that is nearer to the base is called distal link, distal end, distal end. And the end that is nearer to the, or it's towards the end effector is called, yeah, I'm sorry, I mixed it up. The end that is closer to the base is called proximal. Proximal to the base, it's called proximal end. And the end that is nearer to the end effector or towards the end effector is called distal end. And this is how a general link would look like, a link. And these are the joints. Joint 1, joint 2. Right? Yeah, and as far as the modified DH representation is concerned, the first step is the frames are basically attached at the proximal end, always. So each of these links will have a frame attached to them, and the location at which we would be attaching the frames would be at the proximal end for this non-standard DH parameters. Right, and coming on to how to attach these frames, the convention itself. If you take a look at the figure over to your left-hand side, it comprises of two links, as I've said earlier, and two joints also. So this is joint I-1, and this is joint I. And for the sake of simplicity, these are all, it is represented as revolute joints. Revolute joints are, basically what revolute joints are. These are single degrees of freedom joints that will only have a rotational degree of freedom. And it will have 5 constraints. 5 constraints, like it will arrest the remaining 2 rotations as well as all the 3 translations. So the first step in assigning all the frames is the direction of the z-axis. So if the first step is to identify the z-axis. So since this is a revolute joint, over to your left-hand side, this is the axis of the revolute joint. As per the convention, the z-axis corresponding to the link will always coincide or will always be in line with the axis of the revolute joint. If it is a prismatic joint, then the axis of the z-axis will always be in line with the axis of the prismatic joint as well. But it does not matter where you basically attach the joint, because axis can be of infinite length. So it does not matter if you fix the reference frame here, as depicted in this figure. Does not matter if you fix it here. You could also fix it over here, no problem. But the only important thing is to make sure that zi-1 will always be coincident with the revolute joint axis. So that was the first step. And as part of the first step itself, we'll also, coming on to the subsequent joints, there is also another revolute joint, as you can see over here, as depicted in the figure, right? And the axis of the link I, the z-axis of link I would be as such. Over here, I hope you can see that. This would be zi. This would be zi, yes. Zi. So, zi. Earlier we have attached zi-1, zi-1. Yes. And coming on to the next step, again, like whatever I have said earlier, I hope you have identified the distal and the proximal ends. So corresponding to the link I-1, this would be the proximal end, and this would be the distal end. Right? And corresponding to this link I, this would be the proximal end, and this point would be the distal end. And as I've said earlier, corresponding to each of these links, we would always attach the reference frame on the proximal ends. So the zi is basically attached on the proximal end, and zi is attached to the proximal end of link I. Yes. Then the next step is basically to determine the axis of the x-axis, the direction of x-axis. So how to basically do that? So as per the modified DH convention, it says that the axis of zi minus 1 should lie in the common perpendicular or the common normal of zi minus 1 and zi. So if it is difficult to follow, I'll write it down. Axis xi minus 1 should, sorry, yes, the axis xi minus 1 should be along the common normal. Oh my God. Should be along the common normal of zi minus 1 and zi. So axis is xi minus 1 should be perpendicular to both zi and zi minus 1. So like it'll be clear as you do more examples. So for this generic configuration, it will be somewhat like this. The direction of xi minus 1 would be along this link line. It would be along this, right? So I'll depict that. So this would be the direction. Sorry, I'll use a different ink. Yes. This would be xi minus 1. And to get the direction of xi, we would need the information regarding the I plus 1th joint. So xi would be along here, xi would be along the common normal with respect to zi and zi plus 1. That is how you determine the axis of zi. It all depends on the common normal, right? So now that we have established the z and x axis, we basically have the coordinate frames in hand, because the y axis, you can identify the orientation of the y axis using the right-handed thumb rule. But it does not matter because the y-axis does not come into picture for the DS parameter method. So it does not matter whether you actually depict the y-axis or not. As the transformation about the y-axis is not part of DH representation, does not matter. So now what do we have over here? We have the reference frames for the I minus 1th link, Zi minus 1 and Zi. And we also have the reference frame for the ith link, that is Zi and Xi. Now, the objective is to find out the transformation between I minus 1th link to ith link. We need to figure out how to transform this reference frame onto this reference frame successively. So as per the DH parameters, we would only require 4 parameters as opposed to 6 parameters that what is basically obvious. So if you attach the reference frames as we have discussed earlier, like z-axis should lie along the axis of the joint, and xi minus 1 should lie in the common normal of zi and zi plus 1. Then we would only require, one second. Yeah, apologies for that. Yeah, as I've said, like if we assign the frames as per what we have discussed until now, as per the DS representation, we would only require 4 parameters, or rather 4 transformations. So the first transformation is basically the rotation about xi minus 1 axis. And the second one would be the translation along xi minus 1 axis. The third transformation would be theta, the rotation about z-ith axis, and the fourth would be translation along z-i axis. So there are two rotations, xi minus 1 and zi, and two translations, xi minus 1 along xi minus 1 and zi. So if you do this successively, you would be able to transform this frame onto this frame. So it does not make much sense as of now. So I'll briefly describe the procedure. So the first step is to rotate. The first step is to rotate about xi minus 1 by an angle alpha, so that zi minus 1 and zi would be along the same line, or would be parallel, right? So the first I'll use a different color basically. So if I rotate about xi minus 1, this is xi minus 1. The purpose of it is to bring zi minus 1 along zi. So if you can imagine, if you rotate xi minus 1, yeah, the new zi minus 1 would be somewhat like this. The new zi minus 1 would be, would be like this. Zi minus 1. This would be the new xi minus 1, because we are rotating with respect to xi minus 1. So it won't change. It will still be xi minus 1. I'll call it as dash, a single prime. Zi minus 1 dash. Right. So what we have done is that we have basically aligned zi minus 1 axis along the direction of zi through a rotation about xi minus 1 axis. Now zi minus 1, the transformed zi minus 1 and zi are parallel. So we have made the first transformation, right? Now the next transformation is translation, a translation along xi minus 1 axis for a distance ai minus 1. So if the link length, if this link length is ai minus 1, we are basically transforming this entire zi minus 1 frame along xi minus 1, so that it'll coincide with respect to the axis of the subsequent frame zi. So the second transformation would something like this. Zi minus 1 would come here. Sorry, xi minus 1 would come here. Zi minus 1 would be here, right? And due to the fact that this is the second transformation, I'll use this double prime, right? So what we have done is we have translated the I minus 1 frame along xi minus 1 through a distance ai minus 1. So we have completed the second transformation, right? Now, what are the remaining things? Now we also have something called the third transformation is basically a rotation about zi by an angle theta I. So as you might have observed, zi minus 1 and zi are now parallel. And the third transformation, we would rotate this entire I minus 1 frame about zi, so that xi and xi minus 1 would be parallel. So far we have only made zi minus 1 and zi parallel, right? To make xi and xi minus 1 parallel, we would rotate about zi minus 1 by an angle theta I, right? So the third step would be to rotate about zi minus 1 by an angle theta I. So zi minus 1 would still remain the same as we are rotating about zi minus 1. Xi minus 1 would be rotated to the new location. This is xi minus 1. And since this is the third transformation, I'll be using triple prime. And zi minus 1 double prime would still be the same in case of the triple prime case also, because we are rotating with respect to the same axis. And now the only remaining thing to be taken care of is this distance, there is an offset distance that will be taken care of by the fourth transformation, that is translation along Zi by a distance di. So if this distance is di, if we translate along Zi by a distance di, then this frame would be coincident with this frame. The I minus one frame would be coincident with the I frame. So this is the essence of DH parameters, the DH methodology, right? First, we would assign the frames for all the links. Then we would use a successive transformation as the rotation about xi minus 1, translation along xi minus 1, rotation about Zi, translation of log. And the order of this transformation is also very important because these are nothing but matrix transformations. And as you might have, as you can recall, matrix transformations are not commutative. So the order of this transformation is very important, right? So through 4 successive transformation, we have managed to discover the mapping between I minus 1th frame to the ith frame, right? So if you successively multiply all the transformation metrics, so the rotation about xi minus 1th frame multiplied by translation along xi minus 1th frame, the rotation about Israelite frame, the translation along Israelite frame, you will end up with this matrix. This is basically a general R matrix based on DH representation. So a general transformation between I minus 1th frame to the ith frame would be basically a multiplication of these 4 transformation, which would give you this final transformation matrix. So our ultimate aim is to determine all the transformation metrics. So if there are n links, we would want to find out if 0 is the ground link, the ground frame, and n could be the end effector frame. So our objective is to find out the transformation of the nth frame with respect to the 0th frame. This can be obtained by successively multiplying all the reference frame that comes in between. That would be, that would come like 0t1 times 1t2 times 2t3 times 3t4, etc., n minus 1 tn, right? And a general matrix between 2 successive reference frames, 3t4 or 2, 3, does not matter. It would be of this form. It would be of this general form, right? Okay, and as you might have observed, we have a mix of indices. So if you can see, we have a mix of indices, I minus 1 and I and I minus 1 in this matrix. So this is basically a general transformation matrix using non-standard DSA representation. Right? And this is what we'll be using throughout the course. And there is also one more widely used DH representation called the standard DH representation. And as you might have observed, there are no mix of units. See, it's for the transformation from I minus 1th frame to the ith frame, all the indices are basically of the term I. See, it's all I only. But in the case of the previous one that we have discussed earlier, we have a mix of indices, I minus 1 and I. So that is one of the differences between the standard and non-standard representation. And just to give a comparison between the two methods, right? We have an important 4 major differences between the two methodologies. So the first one says, in non-standard DH, the rotation theta I is around Zi axis, and the joint number is the same as the coordinate number. So it's a bit difficult to elaborate that within the context of this course, but I'll give you a brief example. For example, let this be the standard DH formulation over here, and over here I'll give you the non-standard. I guess yeah. So if you take a look at a link, a binary link for a standard representation, or 1 second. Apologies, we have some latency issues, as you might have observed. Yeah, I'm depicting a general link for both of the cases. So if this is the direction of the base or the ground, and if this is the direction of the end effector, and same for the non-standard base, end effector. And if you can recall, like we have, as per the notations, we have two ends. The first being called the proximal end, and the later being the distal end. And same here, the proximal end, and here the distal end. So the key difference with respect to the standard and non-standard methodologies is that in standard, we would attach the reference frame on the distal end. This is where we attach the reference frame. So corresponding to, I'm sorry, this. This is where we would attach the reference frames on the distal end for the standard DH methodology. And for the non-standard, that is what we follow in our course, we would attach it on the proximal end. This is where we attach the reference frame at the proximal end. So this is one of the key differences with respect to the standard methodology, the standard DS parameters, and the non-standard parameters, right? And because of this convention, we have several artifacts that arises. The first one being in non-standard DS, the rotation theta I is around zith axis, and the joint number is the same as the coordinate number, right? So if we have a coordinate like this, z1, x1, and y1, we know the joint angle theta I with theta 1 will always be with respect to z1 in non-standard DS parameters. But in the case of standard DS parameters, it would be something like this. If we have a reference frame, z1, z2, x2, and y2, the rotation about z2 would be something called theta 1. There is basically a mismatch. The joint angle, there would be a mismatch between the joint angle and the reference frame for the standard definition. Whereas in this case, the indices of the joint parameter theta 1 and z1 is always consistent for the non-standard DS parameters. So there are a few trade-offs actually between both of the parameters. Earlier, the only issue with the non-standard would be the mixing of indices, I-1 and I. But everywhere else, the usage of non-standard is much more clearer because the rotation about zi-1 would be corresponding to the index 1 for the joint angle theta, right? And the second point is actuation forces, which is exerted on joint I, is also the same place as the coordinate frame. So if you are moving on to the dynamics, when you come across dynamics, if you want to know the forces acting on joint 1, you only need to look at the forces acting on the coordinate frame 1. Whereas in the case of the standard method, we'll have to look at somewhere else. We'll have to look at the forces acting on joint 0, right? So there is always going to be a mismatch between indices in the case of the standard method. And addressing the third point being the addressing the link's geometric characteristics, such as the center of gravity, are more natural in the system. In the system means in non-standard method. So again, coming on to the diagram, uh, if you can based on intuition, it's obvious that the center of gravity would be somewhere in the middle of the link. Would be somewhere in the middle of the link. If I depict this as CG, right, and on the other side also, if this is the CG, center of gravity, which one would you think is more easier to represent? So if you take a look at this thing, the coordinate frame is actually ahead of the center of gravity. The coordinate frame over here is basically ahead of the center of gravity. So representing the center of gravity, we would always have to use negative directions. We'll have to use negative directions for the standard method, right? But in case of the non-standard DH representation, the center of gravity is always going to be ahead of the coordinate frame. So if you want to represent the coordinates of the center of gravity, you can always use positive coordinates, positive x, positive y, positive z. So this is more intuitive and more clearer in non-standard representation to represent the center of gravity. Yeah. And again, the same goes for link lengths also. So if this link has a finite link, maybe AI, if the link length is AI, and if the reference frame is attached at one of the ends, the link length is always going to be negative, right? Because if this is the positive axis, positive x-axis, for example, link length would always be negative because this is what the link length is, and it will always be negative, something like that. But since this is more natural, since the reference frame is attached at the proximal end, representing link lengths would be more intuitive in the non-standard methodology, right? Yeah, that's about it. And in the fourth point, like what we have already covered, what we have already discussed, it says in non-standard DS there is a mix of I and I-1 indices. But again, that is a small price to pay for the advantages that we get over the standard DS representation. Okay, so we'll go with a simple example of a 2R manipulator regarding how to attach the frames and how to find out the DS parameters. So I'll basically depict a 2R manipulator over here. So this would be the first link. Let this be the second link. And yeah, and the first link #1 is connected to the ground. We have ground over here, ground. Yeah, maybe I'll move this diagram to a different location if this is more convenient. Yeah, we have ground over here. And we also have an end effector here, maybe a grip or something like this. End effector. And we have the second link over here, #2. And we also have two joints. So the first link is connected to the ground using joint 1. This is the first joint. And the second link is connected to the first link using joint 2. So this is joint 1. This is joint 2. Right? And yeah. And what is the first step in frame assignments? We will always, so before that, like I hope we know the basic characteristics of a 2R manipulator. This is a planar manipulator, which can manipulate objects within a plane. So for example, since I have depicted this the 2R manipulator in this paper or in the plane of this board, it can only manipulate objects along the plane of this board. So it has 2 degrees of freedom as well. 2 degrees of freedom manipulator. And how are these? How are the rotational? How are the axes of the revolute joint aligned? So the revolute joints are out of plane basically, right? This is a 2 degrees of freedom robot. So the revolute joints will be aligned out of plane. So if this is the plane of the board, for example, this is X and this is Y, the revolute joint would be perpendicular to the plane of the board. The two revolute joints would be perpendicular to the plane of the board. So I'll just write it over here. R joints are perpendicular to the plane of the boards. Okay. Okay, so we'll get on with the assignment of the frames. So can anyone tell me how many frames would be required to model this manipulator? This is a 2 degrees of freedom robot. So how many frames would be required? Can anyone respond? It'll be easier if you respond here. If don't worry about making any mistakes because it's better to make a mistake here rather than. So Sahil says it's 3. Where are these? Okay, Saurav says it's 4. So where would you attach these frames? So, where would you attach these frames? Can anyone say that? You can use your mic, no problems. Ground, link 1, link 2, and end effector. So I've also got cyan. Cyan day also says it's 2. Yeah. The correct answer is always going to be 4 because if there are n links, there would be n plus 2 frames. We have already seen this in the lectures as well as in the preceding slides. Because 2 frames corresponds to the link. So we have ground. We will attach a frame 0 for ground. And for the link 1, we will attach frame 1. And for link 2, we will attach frame 2. And for the end effector, we will attach the frame 3. So in total, we have 4 frames. So for a general n link manipulator, we would require n plus 2 frames. Okay. I hope that is clear. If you have any questions, please let me know. Okay. I hope that is clear enough. Yeah, you can expect similar questions in the tutorials. Questions may be similar to this. If you are given end links, how many frames would you require so that the end effector, the transformation of the end effector can be mapped all the way to the base. Yes, right. Okay. Okay. So moving on. The next step is to identify the z-axis of all the frames. To locate the z-axis of all the frames. So we'll basically depict or we'll basically plot or draw the z-axis of the known joints. So we know for the fact that the revolute joints are always going to be out of plane. So if this is the axis of the revolute joint 1 and if this is the axis of the revolute joint 2, so it should be plainly obvious that these both axes should be parallel because it's a planar robot. Both of these axes of joint 1 and joint 2 would be parallel to each other because this is a 2R manipulator. Yes, and we would attach the first axis Z1 along the axis of joint 1. This would be Z1, and along the axis of joint 2, we would attach Z2. Right? We also have 2 more joints to be attached. That is corresponding to end effector and base. So that can be done in however fashion you want. It does not matter in what orientation or in what location you would attach. It can be however you want, but we would use the most easiest transformation. So if this is the ground, I would prefer to attach the ground frame coincident with respect to the z-axis of the first link. So the 1 and 0 z-axis are coincident, and the ground's reference frame x-axis. Okay, before coming on to the x-axis, we would plot the x-axis of the known joint. So as I've already depicted, the direction of xi would be common perpendicular would be along the common perpendicular to both ezi plus 1 and zi, right? So if you take a look at the joint z1 and z2 are basically parallel. It's parallel and it's out of the board. So it does not matter in which direction. You can basically choose zi along any direction of the plane. It can be this, it can be this, it can be this. Does not matter, because whatever direction you choose along the plane would be perpendicular to both z1 and z2. Because as per the DH representation, xi should be perpendicular to both zi plus 1 and zi, the subsequent and the current one, right? And the most judicious way is to align the xi axis along the the direction of the link. I'll tell you why though, because if I choose x1 like this and x2 as such, so x1 is along link 1 and x2 is along link 2, and we can also come back to the zeroth frame. So z1 and z0 are coincident. x0 would be, this is the direction of x0, and yeah, one second, this is the direction of x0. And how to choose x3, the end effector frame? X3 would be, sorry, x3, yeah, x3 would be parallel to the end effector. Yeah, x3 would be parallel to x2, and z3 would be parallel to z2. I'm simply choosing this out of convenience only, because if you can recall, if x2 and x3 are aligned, and sorry, z2 and z3 are aligned, and x2 and x3 are aligned always, then the transformation between the second frame and third frame is always going to be identity matrix. It's always going to be a simple diagonal 1 0 0 0 1 0 0 0 1. It's going to be very straightforward. Yes, and now we'll have to look at each of these frames one by one to find out the DS parameters. So if you can recall, there are 4 parameters. We have something called alpha I minus. We have 4 parameters. The first being alpha I minus 1. The second one would be AI minus 1. This is the link length. The first one is link twist. And the third is theta I. Third one is theta I, and the fourth one is DI. And over here, I'll simply depict I being the join number. So, sorry, the link number, I'll write it one by one. This is the links number. This is the twist angle. This is the link length. And theta I is the joint angle. And DI is the joint distance. So for corresponding to the link 1 basically deals with the transformation from the 0th frame to the first frame, right? So in case of link 1, what would be alpha I? Alpha I would be, so I'll just draw the 0th and the first reference frame in isolation, so that I hope it can be more it can be more clear. So yeah, this is Z1. And along the same direction, we have Z0. X0 is in this direction. And X1 is basically rotated by an amount θ1. Because this is a revolute joint, it can rotate however it wants. So the rotation of the revolute joint is characterized by this joint angle θ1, and the rotation of the second revolute joint here, this is characterized by θ2, the joint variable θ2. So what does alpha I minus 1 depict? Alpha I minus 1 is the angle if the angle between Z0 or Zi and Zi minus 1 with respect to Xi minus 1. So as you can see here, the angle between Z0 and Z1 is basically 0 because both of them are coincident. So you don't have to rotate any angle about X0 to make Z0 coincident with Z1. It's basically this is basically is already coincident. So Zi minus 1 would be 0, and Ai minus 1 is basically the perpendicular distance along X0, perpendicular distance along X0 between Z0 and Z1. And again, since as you can see, since Z0 and Z1 are already coincident, there is no need to move along X0. There is no need to move along X0 because they are already coincident. So again, the parameter Ai minus 1 is going to be 0. And what is theta I? Theta I is again the angle between X0 and X1 about Z1. So here this is Z1, and you want to make X0 coincident with X1. X1 is along the link length, and X0 is the ground link. It's always going to be stationary because it's attached to the ground. So you would have to rotate an angle θ1. This angle, you would have to rotate an angle θ1 about Z1 so that X0 and X1 would be coincident. So the joint angle θi would be θ1. And again, di or d1 would be the perpendicular distance along Z1 so that X0, the perpendicular distance between X0 and X1 can be taken care of. Again, since both of these frames are already coincident, you don't have to move any distance along Z1. There is no distance. So this term would be again 0. Now we'll go for the second link, for link 2. Now the transformation is between the frames 1 and 2. So give a perspective, we have the frame 1, Z1 is along this axis, X1 is along this axis, Z2 is along this axis, X2 is along this axis. Now again, coming back to the DS parameters, alpha I minus 1 is basically the angle between Z1 and Z2 along X1. So again, if you can take a look at, due to the particular nature of this manipulator, this is Z1, this is Z2, both of them are parallel. There is no angle with respect, there is no angular offset between Z1 and Z2. So the link twist angle is always going to be 0. And Ai minus 1 is basically the perpendicular distance between Z1 and Z2 along X1. This is X1. So the perpendicular distance between Z1 and Z2 is this distance, physically this distance. So if I define the link lengths of the manipulator as L1 for link 1 and L2 for link 2, right? The perpendicular distance along X1 is L1. So Ai minus 1 would be L1. And θ1 would be the angle. θ1 would be the angle about Now it changes. Now the index changes. Theta 1 would be the angle about Z2, and the angle is between x1 and x2. Angle would be between x1 and x2. Now, what would that angle be? If this is x1 and if this is x2, the angle between x1 and x2 is basically theta 2. Right? So the joint angle would be theta 2. And the joint distance is basically the distance along Z2, the perpendicular distance between x1 and x2 along Z2. Again, since this is a planar manipulator, there is no offset between these two links. If both of the frames are basically lying in a plane, so there is no offset. So in that regard, this becomes 0. There is no offset. Yeah, so now we also require one more transformation. Now the transformation would be between the frames 2 and the frame 3. Frames 2 and frame 3. Right? So what would that be? Alpha I minus 1 would again be the angle between Z2 and Z3. Z2 and Z3. That is again parallel, so that is 0. And AI minus 1 would be the distance, the perpendicular distance between Z2 and Z3 along X2, which is L2, which is this link length. So that would be L2. And theta I or theta 3 in this regard would be the angle between X2 and X3. So since both of them are parallel, there is no relative angle between X2 and X3. So that would again be 0. And the joint distance, the distance, the perpendicular distance along perpendicular normal, the perpendicular distance between X2 and X3 along Z3 would again still be 0 because this is a planar manipulator. So again, this is how we have the DS parameters. And we simply would have to plug in for 0T1 transformation, we would have to plug in the DS parameters corresponding to for the first row. And 1T2, we would have to plug in the DS parameters corresponding to the second row. And 2T3, we would have to plug in the parameters corresponding to the third row. So we can assemble these individual transformation matrices. And once we have all these individual transformation matrices, we can actually multiply them together, 0T1 times 1T2 times 2T3, so that we can get the full transformation matrix 0T3. Yeah, that's about it. That is how you get the DS parameters. And again, there is one more example. This is also a spherical manipulator, but I don't know whether we have enough time. We'll discuss the questions, some sample questions, and if we have time, we can maybe come back to define the DS parameters of a spherical manipulator. This is a 3 degrees of freedom manipulator comprising of a revolute joint, another revolute joint, but both of them are actually perpendicular. So the axis of the first revolute joint is along this direction. The axis of the second revolute joint is along this direction. And we also have a prismatic joint over here, whose direction is along this axis. Right? So if we have time, we can come back and revisit if this problem. So for the time being, we'll move on with the problem solving questions. So that is more important, I suppose. Yeah, so whatever questions that we are discussing here would be more or less in line with the tutorial questions that you can expect. Okay, I think I had a question from Sahil. I didn't see that. So what was the question again? Could you clarify? Could you repeat the question? It says the joint distance is 0, but
Yes.
which joint are you having difficulty with?
Sir, in 2.
2 and 3.
Yes, sir.
Okay, 2 and 3. Because see, if this is a planar manipulator, if you are looking from the top view, okay, I'll just keep it within this context itself. So joint distance is basically the joint distance between 2 and 3, this one, right, is the distance that you would require to move along this direction out of plane, right? But since all the frames are within the plane, you don't have to move any units out of the plane. Is that clear? Because all the frames Z0, Z1, Z2, Z3 are all lying in a plane where the Z component is going to be constant. Or if you consider the plane of the board as Z equal to 0 as a reference, all the frames lie in Z equal to 0. So the joint distance basically takes care of the distance along the Z axis. So the joint distance between 2 and 3 is represented, the joint distance between 2 and 3 is represented with respect to Z3. And since since the frames 2 and 3 lies into the same plane, you don't have to move any units along Z3 because they are all in the same plane. Is that clear?
Yes, sir.
Okay. Okay. So this is a 2D problem. So once you deal with 3D manipulators like this one, you would require the joint distance to be non-zero. So we'll move on to some sample tutorial questions. It says, for a spherical linkage or a manipulator, there are n+2 frames assigned. Right? We have emphasized on the point multiple times. For a linkage, we having n number of links, we would have n+2 number of frames, which includes the base and end effector frame to describe a system. All right. If we use classical or spatial mechanics principle, we need dash parameters to describe the complete system and its arrangement. So what is the correct answer? So in classical mechanics, whatever we have discussed in the lectures, if you can recall, a rigid body on its own without any constraints. So if this is one rigid body, and if this is another rigid body, so like without any constraints, each rigid body will have 6 degrees of freedom, right? Which are 3 translations and 3 rotations, right? So due to the fact that we have n+2 such frames, so each frame corresponds to each rigid bodies. So if we have n+2 frames, that means we have n+2 rigid bodies. Then what would be the number of parameters we would require? What would be the correct answer? I'm getting answers as option A. Yes, that is indeed option A, 6 n plus 2. So 6 times the number of links would be 6 times n plus 2. So that is fairly straightforward. Everyone got the correct answer. So the answer is indeed option A. Yes. Okay, now moving on to question 2. It says, in a revolute joint, what are the kinematic parameters that are constant? So this is somewhat a tricky question. Could you, does anyone have an answer as of now? You can speak up as I'm explaining. If you have the answer, you can let me know. Right. So, okay, again, I'll depict a simple revolute joint. So I'm depicting the ground frame as such. This is Z0, this is X0, this is Y0. And this zeroth frame is attached to the ground. And I have a rigid body as such, something like this. So the proximal end of the rigid body is attached to the ground. And we'll also will have to attach a reference frame to the first link as well. So since the axis of the revolute joint is again out of plane, is perpendicular to the plane. So Z1 would be coincident with Z0. X1 would be along the link length. This would be X1. And Y1 would be 90 degrees using right hand thumb rule would be Y1. Right. And due to the fact that this is a revolute joint, we would require a parameter theta1 to parameterize the orientation of the link 1 or the rotation of the joint 1 with respect to the datum. So we have we have 4 such DS parameters, that is alpha I minus 1, we have AI minus 1, we have theta I, we have DI. Right? These are the 4 DS parameters. And alpha I minus 1 is basically the link twist, and AI minus 1 is the link length, theta I is the joint angle, and DI is the joint distance. So out of these parameters, which of the parameters are constant for a revolute joint? That is the question. Any answers? So once again, the link twist, what I have depicted here, alpha I minus 1, is basically the angle between Z0, right? Z0 and Z1. So we have both of them coincident. Z0 and Z1 are basically coincident. Yeah, Murali gets an option. Murali basically says an option as 3. We'll see whether that is the right option. Okay. So the revolute joint basically keeps on rotating. So this link that I have depicted, it keeps on rotating 360 degrees, however it wants. So if it keeps on rotating 360 degrees, what are the parameters that would remain constant and what are the parameters that would vary? That is the question. That is another way of seeing the question. So if the revolute joint is here at one instant, and at another instant, if that revolute joint is maybe over here, and at a different instant, if the revolute joint is over here, would there be any difference between the angle? Would there be any difference between the angle between Z0 and Z1? No, right? There won't be any difference. It does not matter, irrespective of the. It does not matter how many turns the revolute joint rotates. This parameter or the angle between Z0 and Zi is not going to change. So the angle between Z0 and Z1 that is represented along X0 is basically the link twist angle. That is always going to be constant. Does not matter how many turns the revolute joint makes. So link twist angle is always going to be a constant. Right. Now moving on to the link length, AI minus 1 term, right? So AI minus 1 term is basically the distance between Z0 and Z1 along X0. So distance between Z0, this is Z0, and that is also same as Z1. And the distance is basically measured along X0. The distance between Z0 and Z1 along X0 is basically the link length. So again, irrespective of the rotation, if at another instant if the link is here, if another instant if the link is here, the distance is always going to be the same. It does not change. So it does not depend on the rotation of the revolute joint. So again, link length is again going to be constant. Now the third DS parameter is theta I, that is the joint angle. So would that vary? Can anyone answer? Would the joint angle be varying? So at one instance, this is the orientation of the revolute joint. This is theta1. This finite angle is theta1. And maybe at another instance, this is how the link would orient, exactly 90 degrees. And the angle, if this is the orientation of the link at another instance, and if this is the angle, so there is obviously a change, right? So depending on the relative position of the link, the angle theta1 is always going to be changing. So when the link is fully flat, the theta1 is going to be 0. When the link is something like this, it is going to be 90. When it is like this, it is going to be 180 degrees, right? So again, as per the definition, theta1 is basically the angle between z0, sorry, x0 and x1 with along z1. So this is z1, and the angle between x1 and x0 is defined by the parameter theta1. That is also called joint angle. So joint angle, again, that is always going to be varying because it is a revolute joint. So depending on how the joint rotates, the joint angle is always going to be changing. That's varying. And the final parameter is joint distance, di. So that is the distance between x0 and x1. This is x1 and this is x0 along z1. So it does not matter if the revolute joint is at this configuration or at this configuration or at this configuration. Whatever be the configuration for a revolute joint, the distance between x0 and x1 is not going to change. It's always going to be at a single point for a revolute joint. So again, joint distance, the fourth parameter, joint, having some issues with the pen, yeah. Parameter, joint, seconds. They having some issues. Yeah, joint distance, JOINT. Oh my God. Joint distance, okay, I hope you got the point. Joint distance is again going to be constant. So out of all the options, which one is the correct option? Murali actually says option 3, that is link twist, link length, and joint distance. That is indeed the correct answer. And the only varying parameter, kinematic parameter for the revolute joint is that is always going to be the joint angle, right? And in the case of a prismatic joint, what would be the answer? In the case of a prismatic joint, the prismatic joint's motion is always represented along z-axis. And the parameter, that the distance that we are representing with respect to the z-axis, that is always going to be varying. And joint angle would be constant in case of a prismatic joint. Yes. So the answer is indeed the option 3. Okay, moving on to question 3. It's a fill in the blanks kind of a question. It says the perpendicular distance from xi minus 1 to xi axis measured along zi is. So what is the correct term? We have 4 ds parameters, that is alpha I minus 1, ai minus 1, theta I, ti. This is link twist angle. This is link length. This is joint angle, and this is joint distance. I guess I've already got an answer. I guess I'm getting, yeah. Saurav says the answer is joint distance. Is that correct? Joint, Murali says joint offset. Yeah, maybe I suppose Murali also meant the joint distance. Both of them corresponds to this answer, joint distance. That is also, it can also be called as offset also, no problem, joint distance. Yeah, let's see whether the answer is correct. So the distance between xi and xi minus 1 measured along zi that is indeed joint distance or joint offset. Joint offset or joint distance. That is indeed the correct answer, because we have basically iterated the definitions of all the 4 parameters multiple times throughout the lecture. So we should be knowing what this alpha I corresponds to, ai minus 1 corresponds to, theta I corresponds to, and what di should be corresponding to. So the answer is indeed joint distance. Yes, correct. Okay, coming on to question 4. This question you could probably do with just with the lectures of week 1. This is a simple question. It says, for a given condition, the frame B is rotated about positive y-axis of frame A by alpha. What will be the transformation matrix of B with respect to frame A if the 2 frames are initially coincident in all manner? So we have 2 frames A. Let this be Z0, sorry, ZA, XA, YA, and we also have a frame B, ZB, XB, YB. So it says initially both of them are coincident. So like these two should be merging, like both of them should be coincident. Like I have basically given a offset just to make the representation clearer. Right. So again, the question asks, if the frame B is rotated about the positive y-axis of frame A by alpha, what will be the transformation matrix of B with respect to frame A if these two are initially coincident in order? So if I'm rotating with respect to the frame Y by an angle alpha, so YB would still be coincident with YA because we are rotating with respect to the same frame. XA would be somewhat like this. This would be XA, and ZA would also be rotated something like this. ZA. This would be alpha. This would be alpha. And the question basically asks the rotation matrix corresponding to, the transformation matrix corresponding to this specific transformation. And we already know the transformation matrix is a 4x4 matrix comprising of a 3x3 rotation matrix, a 3x1 translation matrix, and the final row would be 0, 0, 0, 1. And the rotation about the positive y-axis, that is also fairly straightforward. Like if you know how to find it out, it's nothing but it's basically nothing but the direction cosines between each of these axes. So rotation about y along an axis, that would be something like this: cos alpha 0 sine alpha 0 1 0 minus sine alpha 0 cos alpha. We have covered regarding the transformation matrix. The rotation matrix, if we are rotating with respect to x-axis, with respect to y-axis, with respect to z-axis. And this rotation matrix corresponds to the rotation about the y-axis. And which of the submatrix have the same component? So I guess I already have an answer. It says option 5. Is that correct though? Cos alpha minus sine alpha? No, for the y-axis, this is the correct transformation matrix, right? So the answer is option. Yeah, okay, I misunderstood. The option is indeed option 5. Yeah, 1, 2, 3, 4, 5. Yeah. This is indeed the correct answer. Right? In the last week, we have also elaborated on how to populate each of these elements column by column. So if you take the first column, how to populate the first column, how to populate the second column, how to populate the third column for a rotation about any axis. We have already discussed that in the previous week. So the answer is indeed option 5. Check the answer key. Yes. Yes. Yeah. Coming on to question 5. It says the relative position and orientation between two successive links are expressed by, again, like I have given the definitions of link parameters and joint parameters. And I also mentioned that there is a chance of getting it confused. So it says the relative position and orientation between two successive links, right? So like, for example, if I'm giving you two links, this is one link and this is another link. So like we know the relative orientation between the two links is given by some joint angle, maybe some theta or something. Theta 1 or something. And what is this theta 1? This theta 1 is basically nothing but a joint angle. Right? Or similarly, if you are looking from the top, if there is an offset between two links. For example, this is a revolute joint. And the another link would be somewhere around here. This would be joint offset. This distance would be joint offset. So the orientation, the relative orientation between the two links is given by the parameter theta 1, that is nothing but the joint angle, and the relative offset between the two links is given by another parameter called joint offset or joint distance, right? And these two things have something in common. They both have the word joint in common, right? So the relative position and orientation between two successive links are expressed by, I'm getting two answers. Saurav says joint parameters, and Sahil Khan is also saying option 5. So 1, 2, 3, 4, 5 joint parameters. Yes. So yes, option 2 and 3. Really? Okay. Option 2 is joint angle, and option 3 is joint distance. Yes. Yeah. Murali also says joint angle and joint distance. Murali would have been right if this was a multiple correct answer question. If the question asks you to select multiple correct answers, then you would have to select both of these options, right? But if this is a MCQ, if it is a single choice option, you would only need to choose the joint parameters. So these are all correct actually. Like these are all correct. These both corresponds to the joint parameters. So in a way, you are all right. I'm glad that you all got the concepts, right? But in this context, since this is a MCQ question, a multiple choice question, you can only have a single correct answer. So the correct answer you would have to pick would be the joint parameters, right? Yes. Okay, moving on to question 6. This is a true or false question. It says addressing a link's geometric characteristics, like the location of the center of gravity, etc., are easier in standard DS parameters convention. Is it true or is it false? Again, I have elaborated the key difference between the standard and the non-standard. So if this is the standard, sorry, this is the standard, and if this is the non-standard representation, non-standard, we have a link. We have center of gravity for each of these links over here. I'm depicting this as COG, COG. And the key difference between the standard and non-standard methods is the location where we attach the the reference frame. So in standard, we will always attach the reference frame at the distal end. So this is Z, this is X, this is Y. And in the non-standard case, we will attach it at the proximal end. This is X, this is Z, this is Y. And addressing parameters like link lengths and center of gravity is always going to be easy with respect to this convention, because center of gravity and all those things would be a reference with respect to the positive direction. Whereas here we will have to always come in the negative direction. Right. So in that regard, what would be the correct answer? Is it true or is it false? Yeah, all of them are, those who have responded have given the answer as false. That is indeed correct. It would be more easier. It would be more easier in non-standard representation. Right? Not standard, but non-standard. Yeah, the answer is indeed correct. False. Okay. This is a different exercise. It says we have a parallelogram ABCD with coordinates 0, 0, B as 4, 0, C as 6, 3, and D as 2, 3. And this would be rotated about the z-axis by an angle 90 degrees at A clockwise, in the direction clockwise. Now the parallelogram can be described by, we need to identify the new coordinates of the parallelogram, right? I hope you can decode the question. We have a coordinate frame, for example, let this be x-axis, let this be the y-axis, and out of plane would be z-axis. And the coordinates are, the point A would be, second, yeah, the coordinate A would be 0, 0, and the coordinate B would be 4, 0. And what about the coordinate C? That would be 6, 3. Maybe this is 6, 3. This is coordinate C. And D would be 2, 3. So it'd be somewhere in the middle. Yeah. This is coordinate D, which is 2, 3. And this is the parallelogram. Yes. And the question says it is rotated about the z-axis. Rotated about z-axis by 90 degrees at A. So this is the point A, and we are rotating point A with respect to z-axis by 90 degrees. So in the clockwise direction. So the direction is also very important. Don't make the mistake. It can either go in this direction or in this direction. Since it has mentioned clockwise, we should be careful. It has rotated 90 degrees clockwise. So what are the new coordinates? So it's like based on pure intuition, you can easily identify, like if this side is rotated 90 degrees in the clockwise direction, if AB is rotated 90 degrees, it would be something like this, right? AB would be aligned like this. So AB would be, if rotated 90 degrees in the clockwise direction about z-axis, AB would be like this. I'll use a different color like this. Yeah. This would be A dash, B dash. A dash would be still 0, 0. B dash would be -4. Sorry, what it would be? It would be 0, -4, right? B dash would be 0, -4. If we are rotating AB by 90 degrees. Now, what about point C and what point D? How do we find out? So like we can use the concept of rotation matrices, right? So what is the rotation matrix about z-axis? So a general rotation matrix about z-axis would look something like this. Rotation about z would be by an angle alpha would be cos alpha minus sine alpha cos alpha 0, 0, 0, 0, 1. This would be the generic rotation matrix about z-axis. And in the question, it says the angle is 90 degrees, that too in the clockwise direction. So we, by convention, we would always use positive sign for counterclockwise and negative sign for clockwise. So substituting that, we would get cos 90 minus, sorry, it would be cos of minus 90 minus sine of would be minus sine of minus 90, then sine of minus 90, cos of minus 90, 0, 0, it will be 0, 0, it will be 1. So what are these values? Populating these values, this would be 0. Sine of minus 90 is minus 1. We have a minus sign outside, so that will be 1. And this is 0. And sine of minus 90 is again minus 1. Cos of minus 90 is 0. Right? Yeah. And we are rotating the point C. Point C is basically 6, 3. Right? So pre-multiplying that with the rotation matrix, what would be the new coordinate? I'll rewrite it again to make it smaller. The rotation matrix was again 0, 1, 0, minus 1, 0, 0, 0, 0, 1. We have already identified points A dash and B dash. C dash is, earlier it was 6, 3. Now that we are rotating 6, 3, obviously z coordinate is going to be 0 because it's a planar problem. All the z coordinates are 0. And like once we apply the transformation, what would be the new point? It would be 3 minus 6, 0. So point C dash would be 3 minus 6, 0, which would be where it would be? It would be, yeah, x would be 3, y would be minus 6. Yes. 1 second. This would be point C, which is 3, comma minus 6. And what about point D? D would be, earlier D was 2, 3. Now again, the same transformation here, it would be what would it be? So 2 point for point D, it would be 2, 3, 0. So applying this transformation, it would be 3 minus 2, 0. Sorry. 3 minus 2, 0. So the new point would be, again, x would be 3, y would be minus 2 here. This is point D. Three, comma, minus 2. And this would be our rotated parallelogram. So this is how we would identify all the points. So the new point A dash would be 0, comma 0. B dash would be 0, comma minus 4. C dash would be 3, comma minus 6. D dash would be 3, comma minus 2. So yeah, Sahil has already explained it to be option 6. Yes, that is indeed correct answer. So like if you are given a set of points and if you are asked to find out the new points, if all the points are rotated by an amount, some angle, this is how you would approach. You would do the rotation, you would pre-multiply the points with the rotation matrix, and Thus, you would get the new points. All right, so the answer is indeed option 6. That is the correct answer. Yes, coming on to question 9. This is a question that is relevant with respect to the DS parameters. It says find the link twist angle and joint distance di for the given frame arrangement as shown in the figure. So what would you think the correct answer would be? Link twist angle. So what is the link twist angle? What is alpha? What is alpha I minus 1? And what is di? So link twist angle is a new issue that we are getting. Okay, link twist angle. This would be alpha I minus 1 and joint distance di. So as per the definition, what is the link twist angle? Link twist angle alpha I minus 1 is the angle. So alpha I minus 1 is the angle between zi minus 1 and zi along xi minus 1. And di is the perpendicular distance between xi and, sorry, it will be perpendicular distance between xi minus 1 and xi along zi. So in this regard, what is the link twist angle between the two frames? So in this context, there are two z-axes. This is z1 and this is z2. And the angle between z1 and z2 along x1. x1 in the sense like xi minus 1 would be x1. So zi minus 1 would be z1 and zi minus 1 would be z1, zi would be z2, xi minus 1 would be x1. So the angle between xi minus 1 and, angle between z1 and z2 along x1 would be, how much would be the angle? It will be pi by 2, right? If you rotate pi by 2 degrees, pi by 2 degrees along x1, z1 would be parallel with respect to z2, right? If you rotate 90 degrees with respect to x1, both x1 and x2 would be parallel. So alpha I minus 1 would be pi by 2. And the joint distance is basically the perpendicular distance between xi minus 1 and xi along zi. So like whatever be the case, like no matter, it does not matter because both of the frames are lying in the same plane. And no matter how you move along this thing, it cannot be coincident. It can't be coinciding. Because di corresponds to the distance that you move along z2. So suppose if, for example, suppose if z2 is something like this. For example, if z2 is aligned like this, x2 is aligned like this, how do you cover this distance? Distance between z1 and z2. So basically the distance between z1 and z2 is virtually 0 along x2. Along x2. That is the important part. Because these are basically lying in a single plane and z2 can only account the distance out of the plane. So di would be 0 in that regard. I hope the idea is clear. right? Di or the joint distance is always going to be along Zi. In this case, Zi is Z2. So the correct answer is option B, right? Yes, it's correct answer is option B. I guess we have only two more questions, question 9 and question 10. Yeah, now this is a full-fledged problem. You are supposed to find out the DH parameters, the full DH parameters between the frames 1 and frames 2, right? And it's all like there is no joint, there is no very joint angles or joint distances coming into picture because frame 2 is basically fixed with respect to frame 1. So like it's not going to change its orientation at a different instance. It's always going to be fixed. If that is the case given, then what are the DS parameters? So we'll start with the first one, that is the link twist. Link twist, that is alpha I minus 1, right? Which is the angle between Z1 and the angle between Z2 and Z1 along X1. So what is the angle? So if you rotate 90 degrees along X1, Z1 would be somewhat like this. So these are in opposite directions. If you rotate by minus 90 degrees, minus pi by 2 radians, then Z1 would be parallel with respect to Z2. So it should be either minus 90 degrees or positive 270 degrees, 3 pi by 2 radians. So this would be 3 pi by 2 radians, link twist angle. So I'll just depict here for the sake of representation. So if you are rotating 3 pi by 2 radians along Z1 axis, then then Z1 would be parallel with respect to Z2. This is Z1 dash, and X1 dash would still be in the same direction as of X1. So X1 dash would still be in the same direction. So this is the newly transformed coordinate frame Z1 dash and X1 dash. Now the second parameter is link length. Link length. That is AI minus 1. So again, what is the link length? So as per the definition of DS parameters, link length is basically the distance between, perpendicular distance between Z2 and Z1, perpendicular distance between Z2 and Z1 along X1. X1 in the sense the current axis. So we have already transformed Z axis, now already transformed by the link twist angle. So the current reference frame would be corresponding to X1 dash and Z1 dash. And the link twist angle is again the perpendicular distance between Z2 and Z1 along X1 dash. So that is this one, right? This distance, the perpendicular distance, which is L1. So link length would be L1. And the joint distance, what would that be? Joint angle. Joint angle theta I. This would be the relative orientation with respect to xi, x1 and x2. So here x2 is not given, and due to the fact it is also mentioned that z2 is fixed with respect to z1. So there is no harm, like it's implied that z2 will also be in this direction as of x1. Since like what the question means is that like the question says the frame 2 is fixed relative to frame 1. So it is implied that, sorry, what I think I have mixed up. It is implied that x2 would also be in the same direction of x1. And what does the parameter joint angle says? Joint angle is basically the angle between x2 and x1, the newly transformed x1 and x2 along z2. But since these are already parallel, there is no need to rotate about z2 because they are already parallel. So the joint angle theta is going to be 0. And we have one more final parameter, that is joint distance, di. Again, as per the definition, what is di? Di would be the perpendicular distance between xi and xi plus 1 about zi. In this regard, the xi minus 1 would be this x1 dash, the newly transformed, and xi would be x2. This is xi minus 1, this is xi, and zi would be this one. So the perpendicular distance between xi minus 1 and xi along zi would be this one, L2. I hope that is clear, because how we define all these DH parameters, link twist angle, link length angle, joint distance, these are all as per the DH convention. And based on the information that was given in the question, these are the answer that we have come up with. 3 by 2, L1, 0, L2. And in that regard, the correct answer would be option C, I suppose. 3 pi by 2, L1, 0, L2. So I hope you all agree with this. And I would also suggest you to practice some problems regarding the frame assignments of robotic manipulators, as well as to find out the DS parameters, because multiple examples are there in the internet. It's available. You could also ask me in the discussions forums regarding some examples. And be careful that you follow examples only relevant to non-standard DS parameters. Not the standard, but the non-standard DS parameters. So if you can come up with some questions, and if you can solve it, I'll happily go through that in the discussion forums if you post that. So solving many problems would help you to basically assign the frames on the manipulator, as well as to identify the DS parameters. Yeah, so option C is indeed the correct answer. Indeed the correct answer. Yeah, moving on to the final question. It says, while performing successive translations and rotations, we can change the order of homogeneous transformation. Okay, Murali actually asked a question regarding, can you suggest a good textbook for practicing frame assignments? I guess the books that is covered in the syllabuses are all good. I guess if you take a look at the John J. Craig's textbook that is being mentioned in the syllabus, let me go through the syllabus. Yeah, if you go to this about the course section of the course, they have mentioned a few of the textbooks. The Craig's book is very good, and I have also gone through the textbook of S.K. Saha. Both are good books actually. Like all the books are pretty much standard. Like the textbook by S.S.R.M. Murray and Sastry, like the Mathematical Introduction to Robotic Manipulators. That is also a good book. So I would suggest going through all the three books in the references, like the Saha's Introduction to Robotics. Goshal's book is also good, Fundamental Concepts and Analysis. And John J. Craig's, that is a fairly standard textbook for this non-standard DH parameters. And R.M. Murray and S.S. Sastry, that the Mathematical Introduction to robotic manipulation. That is also a good book. I guess for a start, you can actually go through the book by John J. Craig, Introduction to Robotics, because that is pretty much the standard what we are following. Yeah. Yes. Uh, could you see my screen? I think I minimized it and I cannot. Yeah, get back. Yeah, yeah. Okay. Yeah, and if you want me to review any of the problems that you are solving, please reach me back through the discussion forums. I'll be happy to go through the problems that you are solving. Yeah, and moving on to the final question, it says it's a true or false question. It says while performing the successive translations and rotations, we can change the order of sequence of homogeneous transformations. So it basically says that we can change like 0t1 and 1t2 is the same as 1t2 and 0t1. This is what the question basically says. Is it true or false? It should be obvious that the answer is false because these are essentially matrix multiplications. And we know for a fact that matrix multiplications are not commutative. So the answer is indeed false. Yeah. Yeah, and that's about it. Like this is more or less the contents that we have gone through in week 2, and we have also discussed some sample problems, right? So like if you have any suggestions regarding how the tutorial sessions are being conducted, maybe if you want to add some more content or if you want to discuss something else, please let me know. I would incorporate that into the subsequent sessions. Whether you would want more time on discussing the concepts to summarize the concepts, or you would want more time to discuss questions, sample questions. It's your preference. Please let me know. Or is it fine if we continue the current format? Like we just summarize the key concepts that we have gone through the weekend, and later, as a part 2, we would go through some sample questions. If this is fine, I would, you know, I would carry on with the same format. Or else, if you have any suggestions, please let me know. I can, yeah, incorporate that in the subsequent lectures. Okay, Sauru says it's good. Yeah. So it's good, then I'll continue with the same format in the subsequent lectures also. So I guess we have exceeded the time. It's 8 minutes past. Okay, so thank you very much for staying through the lengthy 2 hours of session. Example with 3D model of 6-axis robot. Yeah, why not? Why not? We can discuss that. A 3-dimensional robot, a 3D model of a 6-axis robot. Yeah, it could be easy. But yeah, like whatever your what your suggestion is a bit involved, because modeling a 6D robot in 3D is going to take a lot of time. You can actually get the same principles using a 3 degrees of freedom spatial manipulator, like the SCARA robot and the spherical robots. These are all 3D robots. You could essentially capture all the concepts of the DS parameters using such robots, the spatial robots. That could be done. It's not a big deal. It's fairly straightforward. But modeling and all those things, it would take some time. But in CAD, actually, the 3D model. But it's not a big deal. Actually, it can be done. I'll update you if it's possible in the discussion forums. You can try that on your own. Try modeling. If you are familiar with MATLAB, you can actually try and model a 3D spatial manipulator, maybe a spherical robot in MATLAB. And you can actually see, like, if you change one joint variable at a time, how would the end effector frame would vary. Like if for a 3D robot, you may have 3 joint variables. If you change one joint variable at a time, how would the final configuration would vary? All these exercises could be done on your own. If you are familiar with MATLAB, it's fairly easy and it's fairly interesting to see how these the orientations and all those things would would change. And again, there are good softwares actually. I think it's called Robo Analyzer, I guess. Yeah, something like this. I have posted this in the chat box. This is a software that is developed by IIT Delhi, used for understanding this transformation matrices, the DS parameters, and all these things. It's the software is called Robo Analyzer. You can actually look into that. It's a lightweight, a small kind of a package that can be easily downloaded and installed. It's very useful, very utilitarian, so that you can easily identify, how the transformation changes with respect to each of the DS parameters. It's fairly cool. Yes. Yeah. Again, I don't want to take any further time of your any more further time because it's Saturday. Okay. So with that, I'll wind up the session. Thank you. Thank you very much for attending. Right. Thank you. Yes. Thank you, Melanie. Thank you. So yeah, that's about it. Goodbye. See you next week. Bye. Thank you.